Welcome to the deep dive. Today we are looking at some really fascinating engineering notes focused on, well, the vocabulary of precision transmission manufacturing.
Yeah, it's a great topic. The mission of our deep dive today is basically to decode 5 of these advanced manufacturing terms. We really want to help you understand the actual physical science behind how ultra-precise mechanical parts are made in the real world.
Right, because I think we're all so used to that old school blacksmith approach, right? Like getting metal really hot and just forcing it into shape with a heavy hammer.
Oh, absolutely. But when you are building something like the gears inside a robotic arm, you are operating at a submicroscopic level. The hammer is long gone.
Okay, let's unpack this, because the first problem is really just getting the physical shape out of the raw metal. And the notes mention this term form grinding to bypass what they call standard involute limitations. What does that actually mean?
Well, most standard gears use an involute shape. It's a very simple curve that standard machines can easily cut. But high-precision drives use highly complex, unique curves.
Like the epitrochoid teeth on a cycloidal disc.
Exactly. You can't just slice those with a standard cutter. So form grinding, or profile grinding, uses a grinding wheel that possesses the exact reverse shape of that desired tooth profile.
Oh, I see. So is form grinding essentially using a highly precise, like reverse-shaped cookie cutter on solid metal?
Yeah, that is a really great analogy. You're using an abrasive to just rub away the exact right amount of negative space. But, if you need to carve out a massive amount of metal, engineers use creep feed grinding.
Wait, the notes say that uses a huge depth of cut, but a very slow feed? Why go so slow?
Because by moving the tool very slowly through a really deep cut, you actually combine the rough machining and the finish machining into one single pass.
Oh, wow.
Yeah, so it is perfect for carving out deep slots in a planet carrier directly from a solid blank.
Okay, so grinding solves the shaping problem. But what if the material is, an ultra-high strength alloy? Wouldn't grinding just snap the wheel or warp the metal from the heat?
It absolutely would, and that is exactly why engineers use ECM, or electrochemical machining. They just abandon physical cutting entirely.
Wait, no cutting at all.
None. ECM removes metal via anodic dissolution.
Anodic dissolution. So rather than cutting, ECM is essentially like reverse electroplating to dissolve the metal away without stressing it.
You nailed it. Because there is no physical contact, there is zero cutting force and zero thermal stress.
That's incredible.
Yeah, it's ideal for creating internal splines in ultra-high strength alloys. But once you have the shape, you still have to harden it.
Right, because if you put a raw, unhardened flex spline into a robotic arm, it'll just wear out immediately.
Exactly. But delicate, thin parts will warp in a standard high-heat furnace. So they use plasma nitriding, or ion nitriding. It uses a glow discharge plasma for low-temperature surface hardening.
Oh, and that low temperature is how they control that brittle white layer the notes mentioned.
Precisely. Controlling that white layer is absolutely vital for delicate, thin-walled precision parts.
Like flex splines.
Exactly, like flex splines. Yeah. If that layer gets too thick, the part literally shatters under pressure. Plasma lets engineers keep it microscopically thin.
Okay, here's where it gets really interesting. We have the complex shapes and the hardened surfaces, but how do we ensure these tightly packed parts don't just grind to a halt from friction?
Well, engineers use laser surface texturing, or LST. They use pulsed lasers to ablate microscopic oil retention pits directly onto the sliding faces.
Wait, really? That feels so backwards to me. I mean, wouldn't you deliberately want sliding surfaces to be perfectly smooth instead of bumpy with laser pits?
If we connect this to the bigger picture, it is highly counterintuitive. But those tiny pits trap oil, and that creates fluid hydrodynamic effects.
Oh, so it builds like a pressurized cushion of oil.
Exactly right. That cushion dramatically lowers the starting torque and reduces overall friction in things like harmonic drives.
So making it microscopically bumpy actually makes the whole system run much smoother. That is just wild.
It's brilliant engineering.
It really is. I mean, whether you're managing a manufacturing team or you're simply curious about robotics, knowing these techniques reveals that modern mechanical engineering relies just as much on chemistry and light as it does on traditional metal cutting.
It really is a complete paradigm shift from the old days.
Truly. And it leaves you with a pretty provocative thought. I mean, we currently use microscopic laser pits to manage oil and reduce friction. But, as nanotechnology advances, how will transmission efficiency change when we start engineering these friction surfaces at the molecular level?
That's going to be the big question for the next decade.
Definitely. It's something to think about. Thanks for diving into these notes with us today, and we'll catch you next time.